All right, so we're going to start our lead-in into logarithms, logarithmic equations. Logarithms, I know you haven't seen before, but it's basically another way of writing exponents. So before we get into logarithms exactly, we want to transition away from rational equations, rational meaning fractions, so equations that have fractions in them, which happens when we get variables in the denominator of fractions, to solving exponential equations, which means that we're going to end up having variables in the spot where exponents usually are, right? So we want to be able to solve these exponential equations like this, right? So we need a solution for this equation. Basically, we need a value of x that would make this true. It's probably pretty easy to tell that x is going to be 3. Right, because 3 to the third power is 27. But the way this works, and sometimes it's not so easy to tell, is I want to be able to write both sides of the equation as an exponent with the exact same base. Right? So the real question is, can I write 27 as a base 3 with an exponent? Right? So we get 3 to the x here. 27 we actually can. We can write this as 3 to the third power. If 3 to the third power is 27. Now that both of our exponent bases are the same, it stands to reason that the exponents themselves would have to be the same if these two expressions were to be equal. Since this base is equal to this base, that means the exponents would have to be equal, so I can just take x and set it equal to 3. So we see that x is going to be 3. Okay, and that's all there is to it. We just got to try to make sure that we write exponents with the exact same base on both sides. Common bases, right? For example, this. And so now it's getting a little bit more complicated. What does x have to be to make this equation true? It's not so easy to tell. But if we can write 625 as an exponent with a base of 5, then we'll be able to create an equation that we can go solve. And we can. 625 to the, it can be written as 5 to the fourth power. Now that our bases are the same, we can drop the bases and set our exponents equal to each other. Just subtract 1, divide by 3, and x is 1. Okay? That's our game. And there's just different ways that we can go about doing this. So 3 is the same. We want to be able to write 216 as 6 to a base, base 6 to an exponent, which is going to be 6 cubed. Now, since the bases are the same, we drop the bases, set the exponents equal to each other, and so x is 1. Okay? All right. Number 4 looks like this. And so we want to take 27 and rewrite that as the base of 81 to a power. That doesn't make a lot of sense, right? And we can't write 81 as the base 27 to a power. But we still want both sides. So really, the trick here is to make sure that both sides have the exact same exponent base. So they can both be sort of written down, if you want to think about it that way, or reduced down to base 3 with an exponent. 81 is 3 to the fourth power. So we have to write 3 to the fourth power and raise that to the power of a minus 2. Same thing with 27. It's 3 to the third power, which has to be raised now to the power of 3a plus 1. Now, anytime you raise a power to a power, you just multiply them. So I got to multiply 4 times a minus 2 and multiply 3 times 3a plus 1. Okay, well, I can drop the exponent bases while I do that and just make this 4 times a minus 2 and 3 times 3a plus 1 and go solve that. So 4a minus 8 is equal to 9a plus 3. Subtract 4a, subtract the 3, divide the 5. And a is negative 11 over 5. Okay? So a little bit tougher, but not a lot, hopefully. Right? Okay. Give this a shot. Try to do the same thing. You stop the video. You can start it back up and see how you did. Okay, so what base did you try to rewrite this into? Hopefully 2, because it's really the only one that we can get these guys down to a common base with. So 16 is 2 to the 4th, which we have to multiply by that x. 8 we can write as 2 to the 3rd, which we have to multiply by that 7x minus 15. Making sure that you distribute that 3. Now the bases are the same, so we drop them. So you get 4x equals 21x minus 45 when you distribute the 3. Subtract the 21. Divide the negative 17. And x is 45 over 17. So if that's what you got and you weren't crazy way off base, it's exactly what you should have gotten. Okay? All right. 6 offers up another little wrinkle to this that we got to be really careful about. So 1 over 25. All right. Well, we can't write 125 as the base of 25 to a power. So what can we rewrite these both as the base of? Turns out we can rewrite them as the base 5. So 25 is 5 squared. This is all being raised to the x plus 3 power. 125 we can write as 5 to the 3rd power, which we have to multiply by 2x minus 5. Those still are not exactly the same base. There's a base 5 over on the right side, but this is really a base 1/5 on the left side. So we're going to do something here that is going to make us sort of a little nervous, but because we always are trying to work hard to do the opposite of this, which is keep our exponents positive. We want to keep our exponents positive. But we do know that if we move a base across the fraction bar, it does change the sign of our exponent. So if I take that 5 squared and move it to the numerator, I can do that. It just requires that I make my exponent negative. So now it's negative 2. And while we work very hard usually to make our exponents positive, we do that here because it gives us the exact same base, and it allows us to solve the equation. Now the bases are the same, and I drop them. I just got to take negative 2 times x plus 3, making sure to distribute, and take 3 times 2x minus 5, making sure to distribute. So we get negative 2x minus 6, which is equal to 6x minus 15, and go solve that. Add the 2x, and then add the 6, divide both sides by 8, and we get x to be negative 9 over 8. So this idea of moving bases is allowed as well. Really, all of your exponent rules come back into play. Okay? All right, so we've got 5, 12, and 1/8 as bases here. We're going to want to rewrite these as base 2, I believe. Okay, so 5, 12, we can make this as base 2, 2 to the... actually 2 may not work. What about 8? Yeah, we can do this as base 8. So 8 to the 3rd power would give you 512. The use of a calculator here would be nice. This is already with a base 8 in the denominator, so we're going to move that 8 to the numerator. Remember that that 8 has an exponent of 1. So we got to change that to a negative 1 and multiply that into the negative 4 minus x. So drop your bases. We get 15x minus 3 equals 4 plus x, and we want to go solve that once we distribute, right? Remember, we're distributing. Subtract x, add 3, divide by the 14 and reduce, and you should get 1/2. Okay? All right, try 8 here. Stop the video, work it out, start it back up, and see if you're right. And so, did you get negative 5/3? Remember, you want to reduce when you divide both sides by that 9. But there you go. Rewrite as base 7. On the right side, bring that 7 up into the numerator to make its exponent negative 1. Do some distributing and whatnot. And then solve that equation. Okay? If you didn't get that and you don't understand why, you should have. Make sure you come in and see me during STAR. Okay? That's it. That we'll start there. Next time we'll talk about logarithms. But your homework's out in Canvas, so make sure you go give it a shot.